Swayam Prabha. Digital India. Educated India.
Okay, good morning. So we are looking at the last module of this course. This is to do with a simulation technique. We call this as kinetic Monte Carlo. Yeah. So this is called this kinetic Monte Carlo methods. This is more of a kind of a numerical method to solve stochastic problems. If you recall, when we looked at Langevin dynamics or chemical master equation or Fokker-Planck equation, in many cases, in many simple cases, there was a possibility of arriving at an analytical solution, but those number of cases are very limited in application because majority of the real world problem do not offer itself an analytical solution. So we need to find some sort of a numerical way of solving this problem, and that's where this kinetic Monte Carlo methods are very useful. So what I hope to do in this class is to set up the basis of this kinetic Monte Carlo method, and then how to simulate both continuous as well as jump Markov process using kinetic Monte Carlo methods. So first we will talk about the continuous Markov. And then later on we will talk about the jump Markov process also. So let us consider this the Fokker-Planck equation. A continuous Markov process can be described using this Fokker-Planck equation with the characteristic functions A and B that captures the mean and diffusive, the drift and diffusive part of the process. We already noted that there are some cases for which the analytical solution was possible. For example, if I take A is equal to 0 and B is equal to 1, and we call this as the VNet process. And we also saw that this problem has an analytical solution. So we got P of x comma t is given as 1 by square root of 2 pi t e power minus x square by 2t. So basically the VNet process is basically a Gaussian process, okay, with mean equal to 0 and the variance is equal to time t. Okay, so this we know. So if I want to know all the other properties of the system, we can get mean, standard deviation, higher order moments, and various properties we can find. Now we can also think about creating the trajectory, the sample path itself from simulating this process. So what I mean by sample path here is, so this problem describes if I have a Brownian particle in basically a free Brownian particle, its position is following this kind of distribution. Okay, so we actually can solve for the probability distribution for the particle position itself. Now what I mean by numerically solving this is basically that suppose we want to look at the individual trajectory of a Brownian particle. So that is called the sample path. Okay, and we can actually create. So as we know, this is a stochastic process. Each sample path will be different, but then from there we can get some mean and standard deviation from those sample paths. So so the real question here is, how do we generate sample paths numerically? So, this numerical method is what we call as a kinetic Monte Carlo methods. So, let us say that we discretize time as time is discretized with a uniform interval delta t. So, then time can be written as Ti plus 1 is equal to Ti plus delta t. Okay. So, first we discretize the time. So, now what we want to do is for each Ti time point, we want to know what is the particle position that follows this Wiener process. So, now we know that from the solution of this Wiener process, this is basically a Gaussian random variable with mean equal to 0 and variance equal to t. So, what we can do then is we can write that this random variable x of t is equal to the mean of x plus sigma times n. So, here n is a normal random variate with mean 0 and a variance of 1. So, this x of t is basically a random variable that describes this Wiener process, and it can be given as it is a mean value plus sigma times n of this, but we know that in this case mean is 0 because E of t is 0 here. So, x of t is simply given as sigma times n of 0 comma 1. In this Wiener problem, sigma is nothing but square root of t. Like this. So, now with this kind of discretization, what we can do is we can actually look at the value of x at a different time interval using a normal random variate n with the 0 mean and 1 variance. We have looked at some methods of making this generating random number that is normally distributed. So, for example, Box-Muller method is something that we discussed, from which we can write a subroutine to generate a set of random numbers that are normally distributed. So, now with this, so this is the kind of a propagation formula that kind of tells you how to advance the particle position and create sample paths. Or more specifically, we can say, so from this formula what we can say is that the first time point, let us say x1, this is the position of the Brownian particle following this Wiener process. Suppose this let us say it has an initial condition that the particle starts at x naught. This can be 0 or it can be non-zero. This is the starting point, time t equal to 0. At next time steps delta t, the position is x1, and this can be obtained by the initial position plus square root of delta t times a random number that is uniformly drawn from a normal random variate. So, this formula is written based on this. Now, when you want to go to this time 2 delta t, that is the next time point. So, that will be the previous position x1 plus square root of delta t and then n of 0 comma 1. So, this can be another different random variate. So, at every time step we will create or we will generate a normally distributed random number, and that is used to update the particle positions. So, similarly you can go to xn minus 1 plus square root of delta t n of 0 comma 1. So, by producing this x1 x2 all the way up to xn as a function of time, so this is for delta t, 2 delta t, and this is n delta t. So, if I write time here, this corresponds to delta t, 2 delta t all the way up to n times delta t. Okay. So, then when I plot the time versus the position, Okay. So, this collection of these points, time and x, that basically gives you the suppose if I plot this, you will see that it follows a particular sample path. Okay. So, this is what I mean by the sample path generating numerically. So, this is one particular sample path. Suppose if I redo this entirely with the same initial condition, when I regenerate this trajectory, you will get a kind of slightly different trajectory. Okay, this is another path. You can actually create very large number of such sample paths, and then from this sample path, what we can do is we can get all the statistical properties as a function of time. For example, let us say you create some hundreds of such samples using this algorithm. Okay, then at any given time t, let us say you take time at t, and then you will have many number of the realization for this particle position, and using those number of data, we can find what is the mean value of the position at this particular time, and what is the variance, and what are the other higher order statistical quantities. So, here we show that based on the Wiener process. In the case of Wiener process, we know the analytical solution, we do not have to really do this, but in other cases where we do not have such analytical solution, creating sample path and then getting the statistical property basically takes this kind of an approach. Now, let us take a slightly different case where consider a case where a of x is given as some constant a, okay, so it is a non-zero drift, and then b of x is some value b which is also constant. Okay. So, in this case again by this formula, because this is also, by the way, is also a process that contains analytical solution. So, it would have the analytical solution is given by so when I look at this combination of characteristic functions a and b and then put it in the Fokker-Plunk equation, and when I solve this, I would get an analytical solution for this, for which the position the random variable is again a Gaussian random variable with a mean value of x or mu is given by at, and the variance is given as this is b, is simply bt. Okay. So, again if you want to generate a sample path for this problem, again we discretize the time delta t, and then we write based on this formula. In this case the mean is at, so you will have a times t plus sigma is square root of bt, and then some normal random variate of 0,1. So, the position will have to be updated with respect to, there is a drift term and then there is a diffusion term, and if you want to do this the discretized sample paths, so you will start with x naught at t equal to 0, that is your first initial point, and then the subsequent points can be obtained as x1 equal to x0 plus these two quantities, which is a times delta t plus square root of b times delta t and a normal random variate. So, starting with the initial condition, you update the position for the next time point, the initial position plus this characteristic function which is a is constant times the chosen delta t plus square root of the characteristic function b constant times delta t, and then multiplied by a normal random variable. Okay, this would be the position at x is equal to at a time t equal to delta t, and then subsequent time step x2 you would write as x1 plus a delta t plus square root of b delta t n of 0 comma 1. So if you consider these two steps, these quantities a delta t and b delta t, they are constants in this particular problem. Okay, the only variation comes because of the difference in the normal random variate. So at every time step you are going to create a normal random variate that is distributed as per this. So this number is going to keep changing at every steps. So in this case, since we are having this constant mean term, the mean will actually grow linearly along with some diffusion step. So if you plot this sample path, for this process, you will see that the random process actually kind of grows linearly. Okay, and another sample path would probably go something like this, and so on. Okay, so I am drawing this sample path based on the data points I am collecting here. At every delta t, at every time point, we can update the particle positions based on these formulas. Okay, and then you will get x of t as a function of time. Okay, and those are the individual paths. You can generate hundreds and thousands of such sample paths, and then from these sample paths we can get statistical quantities that we want. So what I have shown here is something like how to numerically generate the realization of the system, the stochastic system's realization as a function of time, and that's what we call as a trajectory or sample path. And we call this as a kinetic Monte Carlo. Kinetic because it evolves in time, and Monte Carlo because we make use of random numbers. Okay, whenever we try to advance a process using a set of random numbers, we use this term Monte Carlo as a methodology. So that kind of justifies why we call this as a kinetic Monte Carlo. Okay, we have a process dynamically evolving, and this evolution depends on certain random number generation. In this case, we used a normal random variate, but there are other processes in which you may have a different kind of random number entering into the problem. So next, what I want to do is I'll talk a little bit about, let's say for a given process, we know how to generate sample paths, a large number of them, and then from those sample paths we apply the formulas of statistics to find mean, standard deviation and other quantities. Any question at this point? All right. Sorry, chat liya. Yes, that's what I'm saying. If, depending upon the process in hand, we may use different kind of random number. For example, I will show later on when we do jump Markov process, we will use an exponential distributed random number. Okay, so depending upon what's the process in hand, we will have it. So here I showed that the solutions are normally normally distributed, so we use normal random variate. There are other problems where there may be other kind of distribution that is possible. Statistical. Let's say that based on certain algorithm, let's say we know how to create trajectories or sample paths for a given stochastic process. Okay, so now what do we do with that? So what we can do with that is that based on generating many of these sample path, we can find the mean and variance behavior of the process. Let's say that we have x of t. This is a continuous Markov process. This is a continuous Markov process, and having E of x and B of x as the characteristic functions. And then what we do here is we generate, let's say we generate a large number of sample paths. I gave two examples for which I already showed how to generate a sample paths. Even if we do not know what is an underlying distribution, still we can also generate sample path. That I will come later, little bit later. But right now let us assume that we know a methodology by which we can create a large number of sample paths for a given stochastic process. We will denote that x1 of t, x2 of t, all the way up to some xn of t. So here we are looking at this process. At the same time point, we have created different realizations. So this point x1, x2, x3 all the way up to xn, these are based on, for a given time, n number of different realizations. Okay. So what this means is, if I plot this, let us say I have got many sample paths, right, many sample paths, x versus t, and now if I take one particular time point t, then from each of these sample paths I have one realization. For a fixed time, I can get x1, x2, x3 all the way up to xn. So that means I have created n number of sample paths, I have chosen a particular time, and I am saying these are the realizations of the process from those n number of sample paths for a fixed time t. Okay. And t could be anything, you can actually choose t wherever you want, okay, at t tending to 0 or very long time, whatever it is. So then we call what is called this ensemble average. Or you could say a sample average. With the symbol x, xt. So this capital X of t is the Markov process that I am interested in, and this suffix n here means that this is a mean quantity over n number of sample paths, that can be simply written as 1 by n. Okay. So you can find, based on these n number of realizations at a given time, we can get an average quantity for x. So that would be this. Now you can also get the second moment. This should be t. Okay. So these are all obtained for a given time t over all the sample values. Now we can write the variance as the second moment minus the square of the first moment. So this is the second moment of x over n number of samples. This is the square of the first moment over n number of samples, and the variance is obtained by this. Okay, so you can put n here also. So if I have a very large number of sample at any given time t, I can find what is the mean and variance of this process. Now clearly you can see that this value of the mean and variance that you are going to report will strongly depend on the number of samples that you have, okay. But ideally what you want is, you want a true average, and the true average you will get if you make an infinitely large number of samples. But creating each sample requires a lot of computational time. We cannot possibly create infinite number of sample paths, so we can only create some finite number of sample paths. Then if I calculate mean and variance from this finite number of sample paths, that would have certain uncertainties, which could be little different from the true averages. So to see to what extent we can say confidently that these sample averages we are calculating based on n number of samples from the true average, we can make an estimate of the errors. So in that case, what we will do is, we will make use of the central limit theorem, where you can see that regardless of this distribution xi which we are generating from this, now this mean that we are getting here is going to be a normally distributed random number. That is the outcome of this powerful central limit theorem, okay. So what we can show is, this mean that you see here will have actually a Gaussian distributed character. So that means, so P of the probability of the mean, the sample mean x of t over n. So this is going to be a normal random variable. So the sample mean that we get is going to be a normally distributed with mean value of mu and variance of sigma square by n, where mu and sigma are for the random variable x. Okay, so what I am saying is, if I have a random variable, I have a random process x of t, okay, and let us say it has a true mean and standard deviation given by mu and sigma, okay, and what we are actually creating, so what we are trying to find out is, okay, let me dial back. So what I am trying to say here is, we have a Markov process with a characteristic function, and through some kinetic Monte Carlo method, I am able to generate a large number of samples, okay, and the sample values, the realizations for a given time t are given here. So over these ensemble of points, I can calculate the mean and the variance, okay. So ideally, this mean and this variance should be the true mean and variance of the stochastic process x of t, okay, and that we can get if I can create infinite number of samples, okay. But like I said, we cannot possibly get infinite large number of sample, we can get a finite number of samples large enough. So we calculate then the mean and variance from a finite sample of size n, okay. Now the question is, how much are we sure about this mean and this standard deviation for a given n number of samples, okay. To answer that question, so what we establish here is that this mean value which you are getting as a sum, an average of the sample value, will have a Gaussian character with the same mean mu and the variance of sigma square by n, where this mu and sigma square, these are the mean and standard deviation of this variables. And what we can show from here, so we report that this the true mean can be written as the sample mean over n number of sample plus 1 by square root of n times sigma n. So, I am writing this based on this particular central limit theorem results, that this is the sample mean we generate from the number of samples, and this is the variance we again calculate from the same number of samples, and this kind of tells you the uncertainty, right. So, this will tell you what is the error involved in the in getting this true mean from the sample mean. This is something we obtain, and this is what we want. This is the true mean of the original random process. Through creating n number of samples, we are able to get this, and then we also associate an uncertainty on this. As you can see, when n goes to infinity, very large number of samples, this term will become close to 0. Then we can say the sample mean we calculated is actually the true mean. But whenever we have a very finite number of samples, when we have very small number of samples, this will tell you what is the error associated with the calculation of the sample mean. Okay. So, this is a very important result, because if you do a kinetic Monte Carlo and get any statistical quantities, this quantity is going to be over a finite number of samples, and then we have to give an error estimate, and that error estimate is basically this term, and that would depend on how many number of samples you have created. By increasing the number of sample, you can minimize the error in your sample mean. That means you can actually be more confident about the closer to the true mean itself. Alright, okay. So, now let us go back to the other problem of for a Markov process for which there is no analytical solution, and then you want to create a sample path. How do we do that? So, if you have let us say a continuous Markov process x of t and the characteristic functions of a of x and b of x, okay. So, right now let us say for this case I do not know, or I do not have the analytical solution, okay. So, now if you want to study the properties of the system, what we try to do is we create trajectories and sample paths for this process. Once we create those sample paths, then we can find the mean and standard deviation of this process as a function of time. So, here what can be shown here is that let us say that we want to write numerically, we want to update the system's state x at t plus delta t using x at time t plus some displacement, okay. So, this is a displacement, that is a change in x over a time delta t, and this can be function of the current x of t and time t, okay. So, you can see that we are trying to write a simple discretization kind of a formula, that we are trying to update the value of x at time t plus delta t from the information of x at time t plus some displacement that can happen over a time delta t. Okay, so that is this. So this is called the displacement. So displacement here I don't really mean it is a spatial displacement. It is basically the difference between two time points. The system's property, whatever that x means here, if x can be let us say a particle velocity, this would be the change in the velocity. Okay, or if you are saying x is some number of molecules or concentration, this delta x here would be the change in the concentration over time delta t. Okay, so this is basically a difference between two time points. It turns out that, I mean, I have given the proof in my notes that regardless of the underlying distribution of x, this displacement will always be a Gaussian random number. Okay, so the proof of this is given in my notes. So we say that this p of the probability of this displacement delta x, this actually follows a Gaussian random variable So what we are saying is we don't know what is the underlying distribution for x, okay, because we don't know the analytical solution. But we are actually setting out an equation to update or numerically generate the random variable x over time t plus delta t using the information x of t with some displacement operator. So this displacement operator basically is shown to be a Gaussian random number. This happens because of the fact that this is a continuous Markov process, and we also apply central limit theorem in this case also. I am skipping the details, but what you can see here is if we know a and b, you can use this distribution to generate delta x as a Gaussian random variable, and then you keep adding this by generating over subsequent time intervals. So this methodology basically gives you a means by which you can generate a sample path for any Markov process, given that you know what's the functional form for a and b. So you would write something like this. So delta x is, if this is a Gaussian random variable with mean of a delta t and variance b of x delta t. Okay, so this is a Gaussian random number with mean a delta t and variance b delta t. So then we can write this delta x as a of x delta t plus square root of b of x delta t times a normal random variable. So at any time t, the displacement operator can be obtained from a drift and a diffusion quantities multiplied by a random variable. Okay, so if you see this looks very similar to a Langevin equation kind of a formulation in a discretized form. That you would have dx by dt is equal to a plus square root of b and then a normal random variable like this. So you can see the unison, the correlation between the Langevin dynamics, the Langevin simulation, and the numerical way of solving this Markov process. So once you have this displacement, so it's very easy to follow. So let's say x naught, this is the initial position or initial value of x, and then you would write x1, that is at time delta t would be x naught plus delta x, which is nothing but a of x naught delta t plus square root of b of x naught delta t times n of 0 comma 1. So, with the initial value you will get the next time point value from the initial value plus the difference operator, okay, which is a times delta t plus square root of b times delta t, and this is going to be a normal random variate which we have to create from this Box-Miller method. And then you can go to the next time step x2, that would be equal to x1 plus again a of x1 delta t. If a, the function a, if a depends on x, then this quantity will keep changing because it depends on the current value of x. Similarly, here you will have b of x1 delta t and n of 0 comma 1, and then you can go all the way up to whatever number of data points you want, okay. So, this would be x of n would be x of n minus 1 plus a of xn delta t plus b of this xn minus 1. So, you would have created a sample path, okay. This is going to consist of one sample path, and then if you redo this one more time, you will get another sample path, and then you can keep doing this over and over, and then you can create a very large number of sample paths. And then based on the equations showed in the just before, we can make use of all these sample values or trajectories, and then get the mean and standard deviation of this process as a function of time. So just to kind of summarize, so what we have done here is we have a continuous Markov process that is characterized by characteristic functions a and b. Okay, if that information is known, then we can make use of this kinetic Monte Carlo method to create a large number of sample paths characterizing the stochastic process. And this kinetic Monte Carlo method is basically a discretization method, a numerical method, where we will make use of random numbers to advance the system's information or the system's dynamical evolution. So what we are showing here is, regardless of, for a continuous Markov process, even if you don't know the underlying probability distribution for the analytical solution, we can still numerically create the trajectories based on this algorithm. Okay, so the displacement is always a Gaussian random variable with the mean and standard deviation given by this characteristic function a and b. Okay, so once we have that, we can create samples of large number, and then from here we can get also the mean and standard deviation and many other properties that is of interest. All right, so I think with that I'll stop here.